My name is Vinitha Ranganeni, and I'm going to be presenting a user interface for collecting Workspace trajectories. This interface is a tool I developed to aid a research project I worked on at the Personal Robotics Lab. I'm an undergraduate researcher at the Personal Robotics Lab at Carnegie Mellon University, where we are working on the algorithms to enable robots to perform useful tasks in environments structured for humans. One of the robots we work with is Herb, the home-exploring robot butler. We have enabled Herb to complete tasks such as stacking cups, pouring water from a pitcher into a cup, clearing a table, and picking a book off a shelf. These tasks were performed in clutter-free environments, but in human-structured environments there's bound to be clutter, making it more difficult to complete these tasks. Dr. Jennifer King's PhD work focused on writing algorithms that manipulated objects in cluttered environments, using non-prehensile interactions. Non-prehensile interactions include movements such as pushing, pulling, or sliding objects out of the way. One challenge was to get good intuition for generating these motions that could be used to guide the algorithm's search. We wondered if human intuition could be used to guide the search. One way to collect data from people is to allow them to physically manipulate the robot to demonstrate how they would complete the task. However, it can be difficult and time-consuming to provide demonstrations to a robot with complex kinematics. We propose an interface where people can provide these demonstrations in a simpler two-dimensional space from the convenience of their computers. This method allows us to efficiently collect large amounts of data. We use the interface to conduct a study via Amazon Mechanical Turk. The goal of the study was to control the robot hand to push the green target box into the goal region, represented by a green circle. Every time the hand was moved, the state of the environment was recorded. The collection of these states described the path the user inputted. When the goal was reached, the user was allowed to move to the next scene. Pushing objects into each other was considered an invalid move. Touching or moving multiple objects at once was considered valid as long as the objects did not touch each other. Trying to move the objects or the hand off the table was also considered invalid. If the user made an unfavorable move, they were given the option to reset the scene and start over. Demographic and strategical information was collected at the end of the study. Some examples of data collected during the study were the number of moves made per scene and the time taken to complete the scene. There was a lot of computation and communication occurring in the background while the user completed the study. The image on the left is what the user sees. If the target object was not pushed into the goal region, the user was allowed to move the hand. If the move was valid, the control was pushed through a black box physics simulator that outputted the state of the environment after executing the control. The state was then updated on the interface. This process repeats until the goal is reached. Everything to the left of the green line is the front end side, and everything to the right is the back end. The front and back end continually send and receive messages so that they can update the environment in real time. If we move up a layer, we see that the front end side is written in JavaScript, and the back end deploys an OpenRave environment. OpenRave is a software that provides an environment for testing, developing, and deploying motion planning algorithms in real-world robotics applications. Flask is a web framework written in Python. The Flask application gets an ID of an existing user or sets a cookie and ID for a new user. Every ID is associated with the user, allowing more than one user to complete the study at a given time. When the user completes the study, the instance of their OpenRave environment is terminated. We developed additional tools that allow you to generate an image of the path inputted by the user or a video of the path. Another tool we developed allows you to create your own environment. You can move objects around, rotate them, add objects, or remove objects. When you are done creating the environment, a file that defines the environment will be generated and saved. While there are many methods to use the data collected to guide the search, we decided to train a random forest classifier. A component of a random forest classifier is a decision tree. In a decision tree, an input is entered at the top, and as you traverse down the tree, the data gets split into smaller and smaller sets. A random forest classifier operates by constructing several decision trees at training time. The result is an average or weighted average of all the terminal nodes that are reached. We specifically trained our classifier to predict a discrete action represented as a xyz velocity and duration that should be executed given the state of the environment. During the search, when a leaf is reached, a default policy is used to evaluate the potential of achieving the goal from the distribution represented at the leaf. The trained model was used as one of the default policies. The user interface was developed in such a way that any of these components can be easily modified or replaced based on the requirements of the study. Source code for the user interface is publicly available on the Personal Robotics Lab GitHub page, and technical details of the algorithm the trained model was used in is available in the paper published by the 2017 International Conference of Robotics and Automation. Thank you for your time.